So we're here with the error function, and then in order to perform this derivation, that is to take the partial derivative of this error function with respect to, say, theta sub j, which is jth parameter. We're going to try to simplify this as much as possible. The first thing that what we want to do is to have the log of the probability that the label is y, given that the feature is x, is to be mapped in two cases, one for y being equal to 0, as well as one for y equal to 0, y equal to 1, and one for y equal to 0. So for y equal to 1, we're going to say it's a log of p, where p is essentially this hypothesis function, where we said that this hypothesis function using this sigmoidal function essentially represents the probability. The probability that the label is equal to 1 given the feature. On the other hand, the second part for the label being equal to 0 is the log of 1 minus p. So therefore, having these two statements combined into one, this one here, we said that that's going to be essentially done by this inside of this bracket. So the whole thing, this error function then is going to be once again same as this, where wherever you see the hypothesis function here is going to be denoted with p, where the p here is going to represent the hypothesis function in terms of the label's probability. Where, for example, the label p with, say, subscript I means that this would be the probability for the ith sample. The probability that the ith sample having, let's say, the value of the probability with the specific input vector x. So the error function is going to be turned into, from this into this notation. Wherever you see the hypothesis function is going to be denoted with this probability. And at this point, what we want to do is once again perform the partial derivative of the error function with respect to the each of these parameter theta sub j. So this is another word of saying this is to take the gradient. Okay, so well, how do we do that? Well, the first thing that we want to do is to have the log of this, and then take the partial derivative of the log of this function with respect to theta sub j, because we have this. And we do this for two cases, once again, for the label being 1 as well as label being 0. So this one, the first one, is the one with the label equal to 1, and this is the one for the label being equal to 0. And so for the label equal to 1, if you can see that this is essentially the is to take the partial derivative of the log of p, right? And then you take the d theta sub j. And so what this means is that, as you can see, that this is going to be equal to essentially 1 over p to dp d theta sub j is what you have, because of this relationship. The log of say f, and then taking the derivative of that is going to be 1 over f times the derivative of f itself. So this is then going to be equal to this for, once again, for this case, and also for the negative case, which is the second term, which is essentially the second term, is same as this, right? That is to take the derivative of the log of 1 minus p, and then take the derivative or partial derivative with respect to theta sub j, is that it's going to be 1 over 1 minus p then take the negative of dp d theta sub j. Okay, so this is what we have for the case of y equal to 0. So we have two cases that by taking the derivative of the whole thing, we divide it into the taking partial derivative of the first term as well as taking the partial derivative of the second term. For the first term is when label being y equal to 1, and the second term with the label being equal to 0. Okay, so just to continue on with the derivation, there are a couple of things, couple of observations that, for example, that the hypothesis function, we said that we're gonna label it with p because this hypothesis function essentially represents the probability of y given the feature, and this hypothesis function is essentially this sigmoidal function. And the identity that we want to come up with is actually 1 minus p. And the way we are going to come up with the relationship is that we are going to have this term divided by this term, which is equal to 1, and subtracted by this p, which comes from here. And if you combine these two terms together, essentially you are going to obtain this, which means that we can then obtain the dp d theta sub j, or partial derivative of p with respect to theta sub j, as just going through the derivation of taking the partial derivative of this p, where p, once again, is this, right? The whole thing as 1 plus e to the minus some, blah, blah, and it's to the negative 1 power. So now with this relationship, you can actually take the partial derivative rather easily. So this is going to be negative 1 because it comes from here. And then it is this, and to the minus 2. And the whole thing is, once again, inside of the bracket is taken partial derivative with respect to theta sub j again. And when you do take partial derivative of this with respect to theta sub j, as you can see, that's going to be exactly this multiplied by taking the partial derivative of this with respect to theta sub j, and that's going to give you minus of x sub j. Okay, so to make everything all clear, then as you can see, the whole thing can be collapsed into or rewritten into this times x sub j. We have a double negative, so it's going to become positive. We have the minus 2 or power of say minus 2. So these two terms, you just multiply it here twice, and this is right here. So the whole thing is rewritten by this. Or what this also means is that, as you can see, this term is essentially p, as we have done here, and this term here is going to be 1 minus p, right? So this means that this is essentially p times 1 minus p times x sub j. And this is what this is, right? Okay, so this means that dp d theta j is p times 1 minus p times x sub j. Okay, so we arrive to this conclusion, that is to take, if you take the partial derivative of this hypothesis function or this prediction, which we call it as p with respect to theta sub j, it's going to give you this. Okay. Okay, so going back to the error function, where the error function is, once again, is the sum of all the samples, and inside of the bracket is the term for the positive label and the term for the negative label, where the p is essentially a hypothesis function given by this sigmoidal function. And when you take the partial derivative of this error function with respect to theta sub j, it arrived to this relationship for positive, and then this arrived to this result for the negative, And we just found this result, right? This result from the previous slide, which came out to be this. Okay, so all we have to do is now merge these two things together. So I'm sort of like repeating myself again and again. Once again, to summarize what we have said, is that the whole thing, or I should say right here, the positive label case and the negative label case, when you take the partial derivative of the first term, it's going to be this, and the partial derivative of the second term is going to give you this, where we also had to derive the partial derivative of p with respect to theta sub j, which we were able to obtain this as a result. So all we have to do is just plug in this here as well as here. So that's exactly what we did, right? So to replace that with this is going to give you this. And at this point, we can also cancel p here. So the result for the positive case is 1 minus p times x of j. And similarly, for the negative side, which is this, replacing this with this, the whole thing is going to be this times the negative times this, which is right here. So here we can also cancel out the like terms there, and the result is going to be minus p x of j for the negative of the labels. Okay, so here we once again have divided into, for the case of positive and the negative of these two statements, when you have this. So to combine these two things together, these two statements, this and this together, all we have to do is to say is y minus p times x of j. Because as you can see, for the positive, when y is equal to 1, this is going to turn into essentially this. And for y equal to 0, this is going to be y equal to 0. So this is going to be essentially this. So mapping, you can sort of say that the combination of these two together can be expressed into a one statement here. Okay, so what? So the next thing that you want to do is, once again, remember what we wanted to do was to use this derivative, or use this dj, the theta sub j, which is this essentially, and then use that to update rule, right? So here, for example, remember we said that that would be essentially theta sub j is equal to the previous theta sub j and negative of the alpha of dj d theta j. So dj d theta j, as we just saw, is this. So that's going to be essentially this. Well, as you can see, because we have one thing that we have to do now is actually to straighten out the sign here. So this one here, by the way, is just this part, but the entire error function has the negative sign there. So to put that into this partial derivative of the error function with respect to theta sub j, we have to actually put a negative sign there. So this is going to be negative of y minus p x of j, or that's going to be we can, you can switch it around and say that's going to be then p minus y x of j. Okay, all right. So this is what we have. So this dj d theta, which is multiplied by minus alpha, is going to be essentially this. Okay, so it's the summation, because we do have summation. And well, actually, I should also put a 1 over n here. Actually, 1 over n is not there, so I should also put a 1 over n there. So this part is going to be p, which is p minus y, times x of j. And for the case of theta having, once again, theta is 0, theta 1, and theta m, the whole thing is going to be a vector notation. So we then have this vector notation for the feature as well as vector notation for the parameter. Okay, so we were able to derive, and what is it that we notice? Once again, that this update rule with the correction, that is, we're missing 1 over n right there. So we should put 1 over n there and 1 over n here as well. So with that correction, as you can see, the entire notation is exactly same as the form that we used for the linear regression case. Okay, so once again, let's summarize what we have done so far. So we have this error function. What we wanted to do is to minimize this error function with respect to theta. So this is how we can obtain theta, which is the parameter that we are trying to have this iterative process or this gradient descent process to converge. And that iterative process is essentially done by this, where theta sub j, the current theta value, is equal to the previous value with this update term, where this update term is the negative of alpha times 1 over m of the sum of this relationship, where the first term here is the hypothesis function, or p, and the second is the label, right? So essentially what this bracket says is that what is the difference between the prediction to its corresponding sample's label, and then it is multiplied by the sample's feature. Okay, so once again, surprisingly, as you can see, this particular bracket, this green bracket, this green box, looks exactly identical to that of the linear regression case. This I should, by the way, this theta here is actually has an m, so this is from I is equal to 0 to m. Okay, I should also put a j there. So this theta, which is a m plus 1 dimensional parameter, is that it's a m plus 1 dimensional vector. And when you have, for example, a jth parameter, right? The jth parameter is going to be updated by this. Okay, so you can do this for, once again, for m plus 1 dimensional parameter. So just to, for example, show that if this is theta 1 and theta 2, and if this is, say, error function with respect to theta 1 and theta 2, for example, you would have some sort of an error surface that looks like this with a global minimum. Okay, so this is where we have as far as theta 1 and theta 2 star is concerned. So with this gradient descent algorithm, somewhere we can start off at some random initial point, and this is going to be coming down to the global minimum by going through or using this gradient descent algorithm as we have done for the linear regression. Okay, so once again, what we have done was that we have defined the cost function. And for this cost function, what we want to do is to obtain the parameter theta by minimizing this error function. So that is what is the theta that minimizes this error function is what we are trying to obtain. And so given any initial point, initial say theta, we can then have a code that can compute and essentially converge, right? And that convergence is done by this gradient descent algorithm. So you can have this like some initial point, and then gradually this is going to be updated by having this second term. And as far as code is concerned, what we had just talked about is the gradient descent code algorithm. There could be some advanced forms of the gradient descent, which is also called conjugate gradient, or BFGS, or LBFGS. All of these other more advanced algorithms are still very much like that of the gradient descent, but here, advantage is that you don't, for example, have to actually necessarily pick what the alpha should be, which is the learning rate. It does it by itself, and it's often faster than the usual gradient descent. Well, the disadvantage is because there's going to be more lines making up the code. It's going to become a little bit more complex. Okay, so that's going to bring down to expanding this binary case into multi-class classification application. So we just talked about, for example, the label being 0 and 1, which is binary case. Let's say that we now have more classes, more labels to classify. So, for example, you could have the email foldering or tagging into, say, those of the emails that has to do with work, having to do with, let's say, friends or family or hobby, breaking into, just not just spam or no spam, but into these multi-classes. Or in terms of the medical diagrams, it's not going to be just say malignant versus benign, but say not ill, cold or flu. So this is a 3-class scenario. And weather also could be also into multi-class situation, like being sunny, cloudy, rain, and snow. So this would be like 4-class scenario type of application. So we do desire using the gradient descent or using the logistic regression using the gradient descent for performing multi-class classification. So how do we do that? So the way we're going to do that is essentially expand the binary classification case. So we just saw that for a linearly separable problem looking like this, that we could perform binary classification by using the logistic regression. But also for the multi-class classification problem, it's going to be pretty much similar. Here for the binary class, we were able to obtain this decision boundary, dividing the two classes using this hyperplane. And for the multi-class scenarios, like in this 3-class problem, we also desire to have these hyperplanes that divides into 3 classes. Okay, and the way we're going to do that is by means of 1 versus all, or sometimes also known as 1 versus the rest. And the way it's going to be done is, for example, suppose we have the triangle as class 1 and the square as class 2, and those of the red or the axis being class 3 samples. Okay, and so the scenario is going to be that we are going to obtain a decision boundary using this logistic regression prediction or hypothesis function that divides between, say, class 1 versus against all. Okay, so these, obviously this one here and these are the class, say, 2 and class 3 here, and this one here is class 1. So there is a decision hyperplane represented by this prediction or hypothesis function. And similarly, you do the same for the square, which is, say, class 2 versus, say, that of class 1 as well as class, say, class 3. Okay? So there is a corresponding, once again, hyperplane decided by this, just like as we've done, like the binary case, using this, the hypothesis function, representing this decision hyperplane. And further, we do the same for, let's say, the class 3, the red class, versus all, which is class 1 and class 2. So we then come up with this yet again, a hypothesis function that would establish this decision hyperplane. So, so once this is done, that is, we obtain, say, hyperplane 1, hypothesis function 1 and hypothesis function 2 and hypothesis function 3. And then the next thing that you do is that if you inject a test point, say, suppose, right here. So this is your test point. And then what you do is that based on this test point, you try to figure out if this, using this hypothesis function, which side that it belongs, right? And obviously it belongs to this one here. So you have certain value of this hypothesis function, right? Because this test function is going to be injected into this. So there's going to be certain value in terms of probability, right? Because this is what this represents, right? This represents, remember, is the probability that y is equal to, say, is y given the feature parameterized by the theta, which is the probability, and that is done by essentially 1 plus e to the minus theta x. So what this means is that given these training values, we establish this decision line and by these parameters. So you can then compute the corresponding probability when you have this test point at this particular location. And so similarly, you can, using exactly the same test point right here, so this is exactly the same location, so you compute the same thing here as well as here. So you have three different probabilities for the same identical test point. And then what you do is that given these three probabilities, what you do is which one has the greatest value. If it has the greatest value using this means that this guy belongs to this guy here, which is class 1. Okay, so that is meant by 1 versus all, or 1 versus the rest. So just to summarize what we have said is that we train a logistic regression classifier so that we obtain this hypothesis function for each class I, so that we can predict the probability that y is equal to I. And so with that, there are, for the case of 3-class system, we have 3 possible cases, right? So for example, we have the h of theta. Well, actually, yeah, so this is not, the I is not the number of sample, but the class I. So you have, say 1 versus h of theta of, say, 2 versus h of theta x3. So 3 possible hypothesis functions as a result of training, right? Training 1 versus all. And so with that, what you do is that you inject a new input x for each of these values and compare, okay? So you make a prediction, and the one that has the maximum value of the prediction or the probability is the one that, which is then a class of I, okay? So we pick the class I, which maximizes this hypothesis function, all of the 3 hypothesis functions. Okay, so that sort of like concludes what we want to say in terms of the logistic regression case. And the next topic that I want to talk about out of the material here in lecture 7 is the regularization in order to solve the problem of overfitting. So if you can recall back in lecture 1, long time ago, we talked about overfitting versus, say, generalization problem. That is, if you have just a lot more parameters than, say, the number of training samples, you're going to essentially be confronted or encounter this overfitting problem, wherein, as a result of this overfitting problem, whenever you do any of these testings using new test samples, the classification performance or regression performance is going to be very, very poor, which means that you have an overfitting problem. Now, so here in this, three plots essentially represent such cases. So coming back to, say, linear regression case, that is the best line fitting problem given the samples. The first one is the underfitting case, because given the number of samples, the specific hypothesis function that you have is rather very rigid. It sort of like gives a preconception of the model that the data should possess. It's going to then produce a very high bias when it goes through when it goes through the testing after the training is done. And similarly, you have the overfitting case, just like here. I mean, here you have the same number of these samples, but the fitting is very well because all of the specific line that's being fitted here actually crosses each of these samples well. But as you can see, there are, the wiggly is much more than, say, that of the underfit case. The problem with this is that, well, this is just, good fitting as far as training is concerned. But when you do the testing with a new, say a sample being here, then the error between this test to that of the say the learned or the trained line fit is going to be just huge. So we say that you have a very high variance because, as you can see, that each of these new samples that's going to be used for the testing, the variance or the difference between or the mean square error is going to be just much greater than, say, that of the underfit case. On the other hand, if the number of parameters is just about right, then the line fitting is going to be just about right. That is, it's going to be between underfit as well as that of the overfit. So once again, the overfitting case is that if we have just too many parameters, the learned hypothesis may fit the training set very well, as I have indicated there, but it fails to generalize with new examples. Okay. So the question is, under the case of this overfitting case, when you have just too many parameters, how do we get rid of the parameters? How do we perform how do we resolve this overfitting problem so that we can just have this just right case? So this resolving process is called, by the way, regularization. That is to be able to control the specific values of these parameters. So to be able to address the overfitting, and addressing overfitting is called regularization, is that, for example, we could have many or high dimensional data with once again small, n samples is this n is just very small number of samples, whereas for each of the feature is also high dimensional. If you have very large number of samples and high dimensional, then you're not going to have this overfitting problem. But once again, if the training number, the training size or the number of the training data is very, very small compared to the, say, feature dimension, where each of the feature dimension is also meant the size or the dimension of the parameter, or the size of the parameter. Because as you can see, typically the way we do is we do the dot product between the parameter to that of the feature. So that means that the feature should have exactly the same dimension, right? Versus, say, theta 0, theta 1 to theta, say, theta sub m. So it's got the same dimension, the parameter. So this means that the high dimensional feature, right, like that of like 100, is actually would be the cause for an overfitting, because you also, if this m is very, very high, this dimension for the parameter should also be very, very high as well. So how do we solve this overfitting problem? So the first thing that you want to do is to reduce the number of features. Okay, so that's an obvious thing. So you could do that by manually selecting the features that you want to keep, or you could also do some model selection algorithm, which I guess we can do that later on. But the other very useful process to be able to resolve this problem is by means of regularization. Once again, that is, we keep the features but reduce the magnitude or the values of the parameter. In other words, if you have a feature, corresponding feature, say x of j, which is multiplied by the jth parameter. If we have the parameter size very, very small, then the end effect is, because you're actually multiplying these two together, the end effect is that if theta sub j is very small, this means that because you're multiplying with the corresponding feature, the feature is going to, the effect of the influence of the feature x of j is going to be very, very small. So it's going to actually work really well when we have lots of features, and where each of these contributes a bit to making a prediction for y. Once again, remember that for the logistic regression case, we essentially have g of the g of this hypothesis function. Sorry, g of the g of, say, theta transpose to that of say x, right? Because this one here itself is the hypothesis function. Okay, where, as you can see, inside of the g, or the hypothesis function, has this dot product between the feature to that of the parameter. Okay, so this is the one that actually makes up this hypothesis function, or one that makes the prediction. Okay, so furthermore, let's just talk about the intuition of what is meant by very small size of the parameter. For example, you have two cases, right? So this is the one with just about right uh, size of the number of parameters. Whereas if you have very large number of parameters, this is the result, which is going to give you, as you can see, the an overfitting situation. So this is the case when we have a very large number of parameters. So this is going to be the overfitting situation. So if we then give a cost or penalize and make, say, theta 3 and theta 4 very small, so that's going to actually get rid of these two terms and make it looking like this, just only having these three terms. So that's going to then bring it down to the green line, or this. Okay. For example, you could have say the usual cost function for the j, but then we add two more terms there, one having to do with theta 3, and another one having to do with theta 4. And how do we then penalize theta 3 and theta 4, that is to make theta 3 and theta 4 very, very small, is by multiplying with very high, say, constant. Okay, so let's say 1000. So because we're looking at this j theta as like the cost function, in addition to have the normal cost function that occurs because of the difference between the prediction to that of the label, right? As well as this additional term having to do with the size of the parameter. And in this case, once again, by multiplying each of these squares of these theta 3 and theta 4 with a very high value, like 1000, this means that whatever the value you have, theta 3 and theta 4, it will be penalized 1000 times as much. So in order to have this to be, because we want to minimize this cost function, is to set the theta 3 and theta 4 to be as small as possible, say very close to 0. So using this relationship as far as this cost function, by adding these two terms together, is going to then give us this effect, okay? That we only have these three terms as opposed to having 5 terms. So once again, a small values for the parameters is going to actually simplify the hypothesis. For example, we can then, by multiplying it with 1000, say, times that of, say, theta 3, for example, square, versus, let's say, well, we also did the same thing, 1000 theta 4 squared and so forth. That's going to actually make these two parameters, theta 3 and theta 4, to be very, very small. Okay, right. So as far as the housing example is concerned, if we have say 100 features, and each of the features we attach with the corresponding parameters, then what you want to do is to have these parameters to be part of the cost function. Okay, so that cost function is going to be injected or represented by this additional term. That is to have some lambda or some constant or coefficient multiplied by all of these, each of these, say, parameter squares, and then you sum them all. Okay. Usually, by the way, the summation is done as far as the way we want to minimize the parameter is that we do not count theta 0 as part of the of this term. We only involve from theta 1 to the rest. because typically theta 0 is considered as as not reducible, is what I should say. Okay, is not reducible. So once that's actually reducible, that is to have the size of each of these parameter value to be small, it would be just these from 1 to say the rest. So this is going to be called, this is term is called regularization. So and the effect is that now given this new additional term called regularization term, you have then this cost function as denoted by this. And so then once again, what we're going to do is to minimize this cost function with respect to theta. So here, okay, what you want to do is to go through the gradient descent again. Now with having this regularization term. So that is, with having this overfitting parameter case, by minimizing the number or by minimize the number of these parameters by making certain parameters to be as small as possible, then this is going to be turning into this blue line. So an overfitting case is going to become just right fitting by minimizing this j function, having this regularization term added. So, for example, we have two cases: the one with regularization done versus no regularization done. So this is when no regularization is done case for let's say three different possible scenarios. Say underfit, overfit, and just about right for say lambda equal to 0. So when lambda is equal to 0, we mean that that regularization is not done. And so as you can see, for no regularization term, this means that the right-hand term, the regularization term is equal to 0. Versus when you have a regularization term installed as part of this cost function, j theta, then as you can see, this one here is much, well, you can actually see here in this case versus this, right? So the end effect is very small, but as far as this one and this one is concerned, in both cases, they are going to be pretty much very smooth function. Instead of having it very, very wiggly like this, wiggly case like this, it's going to be pretty much very, very simplified and without having the line to be very, very wiggly. Okay, so this will be the end effect for the case of say using the regularization term. Now, you can have a different type of regularization functions. We call that as LP regularizer, which is denoted by this equation. For example, the isosurface for, say, LP regularization is that for P, for example, being 0.5, the isosurface, that is that the theta for the P regularization becomes a constant, is that you have this type of isosurface for P equal to 0.5, and this is when P is equal to 1, which is also called lasso. And for P equal to 2, you have a quadratic function that looks like this, and this is when you have P equal to 4. So so when P equal to 1, we say it's L1 norm. And when P equal to 2, we say L2 norm. And for L0, as you can see, is that when is the limit case with P is equal to 0, is that this is going to give you the number of non-zero weights, where this actually represents the complexity in terms of sparseness. It's something that you don't really have to know at this point, but I just want you to know that you have different type of regularization functions where as far as the cost function is concerned, this cost function, because the cost function is having to do with the differences between the prediction to that of the label, and the second term having to do with, once again, the regularization term. You have to actually satisfy these two terms together at the same time. For example, this is the case for L1 versus L2. So this is the case for L1, the lasso case, the quadratic case, and this is the one for L2 case. I should say this is the lasso and this is quadratic. So this is lasso and this is quadratic. So this means that the quadratic is p equal to, say, 2, and this is p equal to 1. Okay, so in L1 versus the L2 case, which is L2 here and this is L1, is that you have this representation where this is the difference between the or we say that this is the data term, right? So this is the data term where without having the regularization term by itself, this would be the where you would have theta, say, hat, right? So this would be the g, so theta, okay, the error function, where this is the minimum. But with having this particular regularization term, this needs to be also satisfied together at the same time. So this is how we then obtain theta star, okay, rather than this, we now have this to be the theta star. And similarly, for L1 case, the regularized estimate would be actually on these two axes, and this particular axis is where these two error functions meet. One having to do with the data, which is this, and one having to do with the regularization. So this is the one that we are looking for as far as theta hat is concerned. So as you can see, the lasso, the one on the right-hand side, tends to generate sparser solution than a quadratic regularization, because as you can see, we only have one particular value which is has to lie on the axis, whereas here it gives you 2 dimension, whereas here you just give 1 dimension. So once again, this lasso or the L1 norm should give you a sparse solution. Sparse being, rather than having theta 1 as well as theta 2, as you can see, you only have theta 2, whereas here you know the solution here is you need to have theta 1 as well as theta 2 together, right? So this one here is sparser than this because you only have one particular value here for the lasso case than that of the quadratic case. Okay, so once again, as far as regularization concerned, in the linear regression case, we choose theta to minimize this error function, where the error function is going to consist with the once again, the data situation with the prediction versus that of the label. as well as this term, which is the regularization term. So if we set, for example, lambda, the coefficient to be very, very large, then, for example, like lambda to be, 10 to the 10th, then what it means is that because we have to, satisfy this relationship as well as this relationship at the same time, that means all of the parameters are going to be very close to zero because this coefficient will be very, very high. The cost is going to be very, very high. So as far as this hypothesis is concerned, where the hypothesis say function happens to be just theta say transpose to that of say x, or theta 0, say x0 plus theta 1, x1, theta 2, x2, and so forth, then all of these are going to be essentially canceled because these theta should be very, very small. By the way, theta 0, x0 is equal to 1. So only thing that's going to be left would be just theta 0 in this case for very, very high value of coefficients. So that means that essentially the hypothesis is going to be just having this constant theta 0 to be left. So it's going to be pretty much flat as a result of choosing a very, very high value of coefficient. So to have once again, this regularization term together to that of the convergence by the data process, that is to have this cross function, j theta, is to once again use the gradient descent. So that gradient descent process is this. Wherein, remember, this is the regularization term. So when you take the partial derivative of j with respect to theta sub j, it also applies to this term. So you take the partial derivative of this term as well. So that's going to give you this. So as far as say theta sub j, well, this is, by the way, you can also divide it into theta sub j and theta sub 0 versus all the rest, right? Where theta j, it would be from 1 to, say, m. So the case for theta sub 0 is that you don't have this term because this is only meant for once again, j starting from 1 to m. And all the remainders of the j from 1 to m, you're going to have this term in there present. So the end effect of this, by the way, is that if you bring this thing to the other side of the equal sign, I'm sorry, to the first term, and merge it into, say, theta sub j, then it's going to look like this. Okay, so this theta sub j is going to be given with two terms essentially, where typically this value is going to be very, very small. Say it's going to be less than 1. So as the theta sub j continues to iterate, right? Iterate meaning that once again you have the theta sub j updated by these two terms. Then, as you can see, the end effect of this theta sub j is that theta sub j is going to continue to shrink. And this is because of this term. And this is going to be done by, once again, the size of lambda. Okay? Whereas this is a term having to do with the update rule without having the regularization term. So this is the one, so this is the end effect by having the regularization term. This is the one without the regularization. And the end effect of the overall iteration is that it has to be this having the first term, the regularization term, as well as the term having to do with the data update only. We could also inject the regularization term as part of the normal equation as well. And the way we can do so is that if you can recall, without the normal equation, without the normal regulations term, used to be say x transpose x times, and then inverse, multiply that by x transpose y is what we had. Now here, the first term, that's where we are going to inject the regularization term, where lambda is the coefficient, and you have this matrix having to do with the parameter. So for m is equal to 2, for example, that's going to be 3 by 3, where you have 1 and 1 there at the diagonal axis. And so this is a result, as a result of performing, say, the error function using the normal equation process. So once again, the end effect of using the regularization term for the linear regression was what we just saw. We could also do the same for the logistic regression case. So for the hypothesis function, for example, when you have these very, very many terms because of, say, high dimensional feature and so forth, where once again, high dimensional feature means that you have many more, many number of parameters, which is going to tend to make it into, as you can see, overfitting situation. So the cost function, which is this, now is going to add this regularization term, just like that of the linear regression, okay? So then we go through the gradient descent once again. So this is going to be, so the additional term, because of the regularization term, is going to be taken care of by going through the gradient. So this is going to become this. And so this is going to be then turned into this, and making, once again, through the iteration, continued iteration, because this factor is going to be less than 1. This is going to continue to shrink, right? So that would be the end effect of the gradient descent using, once again, this regularization term. This regularization term. Okay, in other words, this theta sub j is going to continue to shrink. So, this is the last slide I want to show. We have examples of regularization that's implemented with, say, a very small lambda coefficient. And as you can see, so the let's say the boundary is much complex, whereas as you continue to raise up the coefficient, or the cost being very high for the number of parameters, then this is going to continue to be a little bit more simplified. So this one is lambda equal to 1, and this is when lambda equal to 10, and this is when the lambda equal to 100. So as you can see, that the boundary is going to continue to become simplified. So it has to be just about right. So in that case, perhaps this one would be just about right? So just about right. Whereas this one here would be maybe considered as underfit, right? Because we have a lot of these blue samples that are now classified as part of the red. Okay, so that's the end effect as we overly perform the regularization. Okay, so that's what I wanted to talk about, so we're complete with the topic of the logistic regression as well as regularization. And the next topic we're going to talk about will be the prelude to, once again, the artificial neural net.